Okay, so I'm going to tell you about taking a scientific approach to science education. And so first I'll just cover what I see as the appropriate educational goals and the research-based principles of learning, what research has told us, and then move into how to apply those principles in the university courses and some of the results we see from when we do that kind of research, how to do it better. And then I'll end with talking about what it is really researchers tell us about what expertise in teaching is in the university science level, what it really is, how to be most effective. But before I start, I want to give you a little bit of background on how I got involved in education, and so you in my sort of perspective about this. And it came not actually from my teaching and courses and so on. I came to this through my physics research and working in the laboratory with students. And I would see these graduate students come to work in my lab, and they'd had many years of great success in physics and math courses. But when they were faced with actually doing science, doing physics in my laboratory, they really didn't know what to do at all. But it clearly wasn't a problem with their capabilities, because after they'd been working with me for a couple of years, they had turned into expert physicists. And so when I first saw this with a few, I thought it was some peculiarity about these individuals. But then over several years, I saw, no, this was a consistent pattern that would happen in many, I would see it in all of the students. And so I came to, this is about 30 years ago, I think that there was a real fundamental question here. And so I approached it like a science problem. I looked at what we knew, the research on how people learn, particularly how they learn physics, to try and understand this behavior. And out of that, looking at that research, I came to see there was a reasonable amount known, and enough so that it explained the puzzle. It made sense, actually. It wasn't confusing. It also made me realize there were much more effective ways to teach science than what these students were getting in their normal college, university classrooms. But it also got me started doing science education research. And so then for 20 years, I had two parallel research groups, one blasting atoms with lasers and see how they act, and the other studying teaching and learning. And in both of these, particularly in the education one, doing experiments, collecting data, finding basic principles. And so the two in some levels go hand in hand for me. But in all of this work, I've really kind of focused on the learning of expertise. And by that, I mean learning to solve problems like a good scientist does, what that means and how to best teach it. Now, in the past few decades, there's actually been major advances given new insights on the teaching and learning of this kind of complex thinking like a good scientist. And it's come from the three different areas that the results have really come together in a very nice complementary way. The brain research, I won't say much about, it's the most recent, but the cognitive psychologists who study the basic processes of how the brain thinks and learns. And then people like myself, physicists, chemists, biologists, in those science departments at universities, actually doing research on the teaching and learning of those specific subjects. Now, I'll go into eventually get into a lot more details about what we found about what's most effective, but I want to first sort of say the very highest level result here of kind of a big summary is it's really given us a new paradigm, really of rethinking how this kind of learning actually takes place, and change it from the old model, and still frankly reflected in almost all how most university teaching is done, even though it's obsolete now, is that we have these student brains come into our classrooms and they vary in different ways. And then we immerse them in knowledge and it sinks in to different amounts depending on the brain. And so with that model of learning, then the primary focus of most universities and university science departments is on first deciding what, the knowledge soup that we're going to immerse. That's the curriculum, what topics we teach and what to order. And then the second part is just admitting the best brains, the ones that the knowledge can soak into the best. And that's been the focus. But what research is telling us is that's really fundamentally a wrong approach and it just incorrect. What is correct is to realize the brains are actually not that different when they come into our classrooms, but they're quite changeable. So rather than putting knowledge into sort of a fixed brain, the learning is actually a process of transforming those brains through the educational process. And in fact, you're actually changing how the neurons are hooked up. You're rewiring that brain, and it's within the rewired brain, you have these improved capabilities. And the rewiring happens because of the brain thinking intently about solving problems. And just in the same way that if you make a muscle work hard, it changes and gets better, the brain does the same thing. And if it's intently thinking, figuring things out, it actually wires itself to be better at doing that. And we can actually even see this now in modern brain studies. And an example I have here is two people are in MRI machines looking at their brains while they're interpreting a medical X-ray image. And on the right is a medical student who's just learning how to do this. And on the left is a highly expert radiologist who spent many years interpreting. And you can see how their brains are being activated in completely different ways while they're doing this process. And we actually have some studies that have tracked this as people are getting more expert and see that their brains are changing and how they're functioning as they become more expert in the subject. Okay, so that's really the sort of highest level picture of how you need to think differently about learning. Now I'm going to move to applying these principles of learning and what we do and the kind of results that we measure in these research and actual university science courses. Now, there's actually been, it's not widely known, but it has substantial, many hundreds of studies like this that look at teaching and learning and do experiments. And I'll give you a few examples, but the basic idea of almost all of these is that they think of tests which actually call on the students to to make decisions in a given problem, what decisions they make, and compare those with the decisions in solving this problem that a scientist in the relative field would actually make in thinking about the subject. And so once you have a test that probes that, then you teach the students in different ways. And usually it's the standard lecture where they're supposed to listen to a faculty member talk about the subject and explain what knowledge they should have and how they should solve problems. And then the second method that I'll call research-based, is really giving the students some, selected situation scenarios, and then having them practice making the decisions and figuring things out, followed by feedback and instruction from the instructor. And so, you can do these in different ways, different times, and so on. But this is the basic methodology used in the great majority of these studies. Now, so I'm going to show you a couple of specific examples, but this is a general method that what represents the kind of research-based teaching and the kind of results one sees. One experiment I was involved with. So this is looking at teaching introductory physics, a very large course with nearly 1,000 students in different sections that's required for all the science students and all the engineering students at University of British Columbia. And so we took 2 sections that carefully measured and so on, that the populations were very nearly identical. And then the 2 sections were taught in 2 different ways. And I should say this experiment was really to learn, to study not what they learned over an entire course. There are other experiments to do that. This was just focusing what they were learning from the classroom experience. And so that in one of these sections, the class was taught by someone who was really was a standard lecture course, someone who's very experienced professor, been teaching this way for many years with good student ratings. The other section was taught by someone who was a relatively new PhD, but had been in physics, but had been trained in my program in these research-based methods of teaching. And the 2 instructors then agreed on the same material to cover in the same amount of class, 1 week of classroom time. And then the students were given a surprise quiz right at the start of the next class to probe how much of what had been covered they learned in the previous class. And so here's the results from the 2 sections. This is so long here. This is their score on this test, and this is the number of students. So the histogram of the results, and you can see there's a profound difference. A standard lecture class in red, the distribution of the experimental or research-based teaching class on right, and the right here. Now, the difference here is actually probably somewhat bigger than you even appreciate at first, because on this particular test, random guessing would give a person a score of about 3. And so you really have to look at the amount of learning they have, is how far above 3 they scored on this. And when you realize that, you realize that the learning from just listening to the lecture from a good lecturer is really tiny. And we see this in many other examples. And the other thing that's important to recognize is that the research-based teaching is really better for not just, the weakest students or the strongest students. It's really better for the entire population, the entire, you can see the whole distribution has moved up. And this is really just because, this is the way the human brain learns, and learns to make decisions through practicing thinking about things. And so that's, it's really better for all the students, and really much better here. So what actually happens in the experimental class, I'm going to assume that most of you know, experience what's in the traditional class, the professors talking, the students are listening and taking notes. The experimental class, first the students have a short preparation ahead of time. The assignment they do that just gets them the basic facts and terminology before they ever come to class. Don't need to spend class time on that. But then the classes are built around having the students answer questions, solve problems. And so For example, in this one, they're learning about electricity, and so they have a basic circuit with a battery and light bulbs here. They have to predict what's going to happen to the brightness of this bulb when this switch is closed. And they have a set of choices that they have to think about. And so first thing that happens, each student individually has to answer. And so they have some technology that we use these little clickers, but nowadays most people use cell mobile phones to do the same thing. So the student has to select what they think the answer is and choose it, and then the instructor's computer records who they were and what their answer was, and in real time shows the distribution of answers from the students, and with a simple app. Now, the students at that point, they're not told the answer, or especially not even shown the vote of others. They're then called upon to discuss with their neighbors. So this, is a class of about 250 students. So it's a great big lecture theater, but the students around on each side, they have to discuss with them, and then they re-vote after hearing from what other students think. But while they're doing that discussion, the instructor's going up and down the aisles, listening in on those conversations and getting an idea of of the snapshot of the students thinking about this problem. Then, and only then, so that takes a few minutes, and then instructor will demonstrate or show the results of what actually happens. But then the instructor will start talking, giving feedback, but now very targeted feedback to the students based on what they've heard and what they see the vote. So talking about, which models of electricity the students had, and reasoning was correct, and more importantly, which was incorrect and why. That's really where most of the learning takes place, is when people have thought about something and then they find out what parts of their thinking's incorrect and how to change it then going in the future. So that's the basic idea of how this teaching works. In this course, it was, there are some physics things and more mathematical and more approaches. Then one wasn't using these so-called clicker questions, but students would have to have worksheets that they would write out, but again, talking with each other, and then fill out individual sheets to turn in. So during this, if you think about what's happening in this question in terms of kind of the students' brains, they're having to practice think like physicists, make decisions like a physicist would. In other words, if you think about it, they have to think about their conceptual model of how electricity functions and what it would be, and therefore what would be happening in this particular situation. They're having to test their conceptual models by justifying them to other students and then seeing how their predictions compare with what actually happens. And they have to critique the reasoning, both of themselves and their fellow students. So at a basic level, this is the same kind of thinking that's done by physicists or by scientists in general all the time. And so they're exercising their brains, thinking like scientists and getting feedback to do it better, and improving it in the process. And they're getting guiding feedback to improve their thinking. They're getting it from other students in the discussion. They're getting it from the now highly informed instructor as well. And so that's the kind of mental thinking practice that is really changing the brain and developing its capabilities, and why you can get these great improvements in learning through this kind of process. Now, just to show you, it's not just physics. This is from computer science courses at UC San Diego, where they adopted this. So here it was the same instructors, but and also this is looking over the entire course, looking at the failure and drop rates. And so the instructors, these 4 kind of core introductory courses they teach, they first taught it in the tradition, well, they had been teaching it in the traditional way, and then they switched their teaching to being doing much more just the same kind of things I just talked about, of giving students a sets of problems and discussions in class. And you can see here that the drop and failure rates dramatically decreased in all of these cases. So here, lower is better. You want everybody to succeed in the course, and you can see that they did, after they converted, they get much better. And so you have the same instructors teaching it, but they're using better methods, and they now have about 1/3 the failure rates they did before. So this is, again, different area, different measure of student success, but dramatic improvement using these research-based methods. Most of the research has been done in introductory science courses, but my own group has, and a few others have worked at the more advanced levels. And then just to show you the same basic ideas, how they work there. This is, we now have most of the courses for the physics majors at Stanford University, so their 2nd through 4th year, have now actually converted to teaching this way as well. And and I actually have examples all the way up through advanced graduate level courses. In those courses, because they're smaller classes, they're much more technical, mathematical, and so they're usually, you have the students working through complex worksheets where they solve complicated problems. But they're figuring them out as they work through, and working in small groups to do that. And so the structure of those classes, and really the basic structure is the same in all of these different classes across all different disciplines. The same basic approach works, where the instructor will, the students have to do some initial preparation before class, a little bit. The instructor will then give them the problem. They'll work for 10 or 15 minutes in these groups, while the instructor is circulating, monitoring how they're doing, answering targeted questions, but mostly monitoring how the groups are working and what problems they're having. And then the instructor will bring the whole class together to give feedback to them, capture the ones that are slower, or moving more slowly, bring them up to understanding, talk about sort of resynchronizing the class, bringing people up together, and then the students will then go back to working on the next section of the activity, and the class will just go through the same basic pattern through the time that they have. And this, if you think about it, this actually, people are now finding it's not a big change to switch to virtual learning, doing the same way. But what's happening here is this, rather than being at small groups distributed in a classroom, these are Zoom breakout groups, actually, where the students are working in groups of typically 4 in class, and the instructors jumping around between those breakout rooms and bringing the class back from the breakout room to the whole class and talking about, and then going back into breakout rooms. The key features are the students are thinking, they're practicing expert reasoning, and the instructor is giving targeted feedback and guidance and new knowledge that they need to make progress as they're working through it. Okay, so we have roughly about 1,000 research studies in total. They're across the undergraduate science and engineering disciplines, comparing this kind of sometimes called active learning or research-based teaching with the traditional instruction. And they consistently show that the results are really dominated, the results in student learning are really dominated by the teaching methods, not any other aspects of the teacher. They consistently show greater learning and lower drop in failure and dropout rates from the research-based instruction. Now, I'm now going to switch to sort of the teaching expertise. What I mean by that is, what do we know about really all the details of really making these methods work? Because you don't get these big changes like I talked about. They don't come automatically. There's a lot of things the research says you have to get right. And so that's really illustrating my summary of sort of all the research across these many different studies, trying to give you a very succinct summary of what's captured in them. And so what's important here is in the middle, where the students are learning because they're practicing thinking, practicing making the decisions of scientists with good feedback. And then all of these boxes represent lots of research that goes of what has to go in to both the design of the instructional activities, what the students are having to do, and the implementation, and also in what kind of feedback they're getting. So first, just starting with, when I say good feedback, this is something that's studied, different kinds of feedback, different ways, and it has to be timely, specific, and actionable. And what I mean by that is that you're trying to improve how people are thinking. So it's got to be timely enough so that while they're still remembering how they were thinking about something, you have got feedback guidance on that thinking. And so it's got to be specific in terms of, okay, this aspect of the thinking and what's wrong with it, and it's got to be actionable so they see not just what's wrong, but then how to change it to be better in the future. And so, taking some big exam and then 2 weeks later or 3 weeks later, finding out what score you got on the exam, that really does not help people's learning very much, because it's too far from when they took the exam. They don't really remember exactly how they were thinking about the problems. It's just a score. It's not specific to tell them what was right and wrong about their thinking and what to do better in the future. And so that just doesn't work nearly as much as having a student actually working on a problem, thinking about it, and then getting feedback in the classroom in that time on what aspect of their thinking to change to do better. Okay, but each of these things then goes into the design of the activity, the disciplinary expertise. I'll talk a little more about what that would mean. These things that I won't have time to talk about, but I'll just quickly summarize in that you're giving the student some task, some problem to figure out. It's got to be at the right level and that connects up with their prior knowledge and then builds on that. So I can't, it's complete waste of time to give a beginning student a problem that's way too hard for them, way beyond anything they know. On the other hand, it also can't be too easy. It's got to be challenging, but possible, and build on what they know. It's also got to, it's really important, the issue of motivation, because what we know is that people have to be thinking really hard about it. It's hard mental work. And so they have to see why it's valuable and interesting to put in all of this effort to learn. So you have to think about the motivation quite a lot as well. And then there's some things about the brain constraints. And so I'll go through some of these things, this one and this one a little more in detail, and then say a little about, the research tells us a lot also about the implementation, the kinds of questions and deliverables that you need to have them do, and the social learning aspects. So I'll talk more about that. But so if this page in some sense defines teaching expertise. If you, at least at the university level, a teacher who understands the practices and principles that research has shown are more effective and contained in all these little boxes here, they'll be going to be more effective in learning, in the same way that a medical doctor, if we now have established, if they have certain knowledge and practices that they know about and follow, their patients are going to get better, more effectively than ones who don't have that kind of expertise. So let me go on here then and talk a little more about what's in some of these boxes. And I'll start with the disciplinary expertise that have to go into designing the activities. And this connects up with something my research group has been working on quite recently, looking at how good skilled scientists and engineers, and now also medical doctors, how they solve authentic problems. And we find that they're that makes a series of decisions with limited information. And what we've been surprised to learn is it's the same set of decisions. There's actually 29 of them we've established across these different fields. And so across all these different disciplines, they make the same set of decisions, but how they make the decisions then calls on the specialized knowledge in these different subjects. And so I'll give you an examples of these kinds of decisions that go into the solving problems, because these are the kind of what goes into the subjects to have the students learn to think like scientists or engineers, is really they have to practice making these decisions. And so if you given in any field of science you want the students to master, you give them a problem where, for example, here's the problem, they'd have to decide what concepts of the science are relevant in that problem for solving, whether it's physics, chemistry, or physics problem, etc. They need to look at that and decide, like a scientist would, what concepts should I use? What information is relevant and what's irrelevant? What's needed to actually solve it? So what simplifications or approximations are appropriate to make in the problem? What are potential solution methods to pursue, and what a plan of solving the problem would be? How to break the problem into appropriate pieces. These are all things we see that scientists are always doing. And when one gets to a final conclusion, then how can it, or tentative conclusion, how can I test that to see, does it satisfy all the necessary conditions? Now, I just listed a number here. There's, like I say, there's 29 of them, but the ones I've chosen are intentional because if you think of the typical problem that that students are given in the textbooks or on the exams, those problems have explicitly removed all of these decisions from solving. It's the textbook or the exam, it's testing on a particular concept. So the students don't have to decide what concept to use. They're been told, we're going to give you a test on this. They never have to decide on the information because they're always given exactly the information they need and only the information they need to solve it. They're told, to what, approximations, neglect friction or neglect the various things to neglect or to include. Those are always explicitly stated. Real problems in the real world don't have it that way, and so we're kind of removing the in the instruction, you're removing the practice of thinking like real scientists. And so getting back to my original point, got into this of why can these students do so well in these courses and not be able to do actual physics? This is exactly why. What the courses are teaching them is not to think like scientists, and to learn to think like scientists, you have to have them practice making the real decisions that real scientists make. And so that's the disciplinary background that goes into designing the problems that students have, so that they not just learn knowledge, but they learn how to use that knowledge in real contexts. Okay, so I'm now going to just jump ahead and say a little about some basic ways the brain works, because these are important in the implementation and very often neglected. Most instructors don't know about them. So it has to do with how the brain remembers and processes things. So there's the first aspect is the long-term memory, and this is supposed to be represented by this box. It's got a very large capacity. We can remember many things and remember them for a long time. So what the cognitive psychologists call long-term memory, that's what most of us think about is what memory is. But it turns out there's another aspect of the so-called short-term working memory. And this is like a buffer in the computer that information has to go through this short-term working memory before it gets into long-term memory. But the short-term working memory, it's very different. It has a tiny capacity. The typical human brain is something like 5 to 7 items is all. And it works on time scales of minutes. And so the sort of in the normal classroom, it's extremely relevant to what's happening there. And it's really the number of things the brain can pay attention to at one time. But it turns out that it's really important because it's sort of, you can't get into long-term memory unless you go through this. And so when you hear, or your brain hears or sees some new thing with this very limited capacity, it will push, actually, some new thing comes in, it pushes out something that was there. And so that thing never gets into long-term memory. And so you have to realize that as you're trying to have students learn, any new thing they pay attention to has a cost because of this tiny capacity. And so in a typical class, that's really important, that any, beyond this very limited capacity, new stuff that you have come in actually pushes other things out, and so reduces learning. And so some of the ways this happens in the actual classroom is in the university setting, and lecture theaters and so on, that the split attention when if students are actually, on their computers looking at other things, or so often I see in classes at Stanford and other universities in the US that students are getting bored, they start looking, checking on their cell phones, checking email or text messaging and so on. This splitting the attention between what that and the material of the course, it's just a disaster for learning, because this split attention, this working memory uses up, they get used up, they're paying attention to that. The material they're supposed to be learning, you want to be learning, doesn't happen at all. But it turns out there's a lot of things the instructors can do that also hurt the learning here, using a lot of complex jargon that kind of overwhelms and fills up working memory. And so they just don't have the capacity to the more important things than the jargon get pushed out. And so anything that gets attention, so fancy pictures, a lot of times instructors will show illustrations with a lot of fancy, attractive pictures just because they look nicer. The trouble is that draws students' attention, and anything that takes up more attention, even things that like jokes and little amusing stories, those actually hurt the learning of the core material. And this is an aspect that I have the most trouble when I tell this, that both students and the teachers will complain about this, because the teachers will say, oh, but that's the only time the students are paying attention to me. And the students will say, oh, that's the only time I was paying attention. And that's the exact point, is that because your brain has this very limited capacity, if you're paying attention to something about that joke, yeah, the students learn the joke, they'll remember the joke. They don't remember anything else the instructor was supposed to be teaching them that day, though, they don't remember the science. Okay, the other thing about the brain I want to just quickly mention is the problem with long-term memory is not so much, it's hard getting things in, but it's even worse getting them back out, the long-term recall. And that's because you put stuff in, but then as you learn new things, there's interference in recalling the old things. The new things interfere with that. And so it turns out that where this comes in is the basic idea of, okay, I'm going to teach them the material in chapter 1. They're going to be tested on it. They do okay, so that's done. We now move on the material in chapter 2 and chapter 3, as if these things just add up without interfering with what happened. And it just doesn't work that way. The chapter material in chapter 2 and 3 actually interferes with the people being later able to remember what's in chapter 1. And so it turns out that the way to avoid that interference is periodically to briefly come back to what was in chapter 1. As you're learning chapter 3, 4, and 5, go back and spend a little time making them think back about what was in chapter 1, and maybe in the homework or on the testing. And that then greatly reduces the interference in the later long-term recall. So that's just some lessons about how the brain works that are important for being good teachers. Let me just, I want to finish here quickly so there's time for questions, but say just a little bit about what we know, research on the implementation that's important. On the tasks, it's good when you have designing it, you have to have very clear deliverables for the people in terms of when they're giving some problem to the students to work in their groups. They're going to be clear deliverables, both the group and the individual that they've got to be producing. And then also this aspect of social learning, the having working groups and doing this. Why is this valuable? Well, this has actually been studied a lot, but it's because, many times instructors, I'll talk to them about the value of having working with groups, and instructors just can't believe that talking to another student about something could be better for their learning than listening to the instructor explain the answer. And we actually have done studies, and you can look up some of our papers we've done, and then that I've done with others, really showing that this actually is the case, that students learn more in some conditions by talking to each other than they do from hearing the expert instructor explain it. And the reason is pretty interesting. The cognitive science people have studied this quite a bit. And it turns out that when you're trying to explain something or teaching something to another person or evaluate their explanation, your brain actually processes in a different way. There's different cognitive processes that come in this social interaction. And so our brains actually work in a different way that actually support learning better. And so that's just kind of important to know that through that social interaction actually has the brain function differently that supports learning more effectively. So, okay, so I'm just going to finish up here so there's time for question. I've just given you a little snippets of this, but the overall picture is that we really have, in the last couple decades, really, that have research that shows how to have students learn much better in the university classroom, actually at all levels, but particularly the data is particularly good on the university classroom, that's much more effective than the traditional lecture approach. And we not just have data, but we have principles and that we understand why this happens. And in terms of really having students learn to think and solve problems more like good scientists and engineers, and how to teach that more effectively. And I'll leave you with one last, I'll give a question that many are thinking about, even if they're not told, or even if it doesn't get asked. But after I give this talk very many times, I get questions in this form of, the faculty saying, but you're talking about these lectures and they can't be all that bad because look, I was taught that way, and look how great I am, or how my fellows faculty are. And I just like to point out that bloodletting was the medical treatment of choice for about 2,000 years, and it was supported by exactly the same logic and exactly the same science or bad science. And the point is that you don't have a comparison group for your brain. If you need to have an identical twin who was taught in a different way and then compare. And I would argue that in that case, you'd find out that actually they could have been more successful if they'd been taught this better way. The brain can learn on itself, but this is just how to have it learn better, and for many be successful for many more students using these research-based methods. So with that, I'll just stop, and I'll say that since I've covered lots of things in a hurry, I've probably overwhelmed your working memory. So I'll make sure the slides are available so that you can look back at them. And here's some of my favorite references, some books on the basic ideas of the research on learning, how to apply it in different ways at a higher level. And then this website here, we have a lot of resources about implementing specific methods and techniques and dealing with specific problems you run into in the university science classroom. So thank you for your attention.
Thank you very much, Dr. Carl Wieman. We have a few questions put forward to you, and I have one question of my own as well, which I'll ask last. If I would like to suggest that if there are those who wish to ask Dr. Wieman in English, please go ahead you can raise your hand and ask the question in a very succinct, brief manner, because we would like to have as many participants being able to ask the questions possible. And but I'll just start with a few questions that are put forward. Here, one question is, how can you measure standard instruction within time limit? How can you measure standard instruction within time limit?
So what I think and I may be misinterpreting the question, but the way I think I'm interpreting this is that if you have a fixed amount of time, how do you, how can you teach this in a different way? Because the standard instruction, it seems like you can cover the much more material if you're giving a traditional lecture and so on. And it's just, you have to think, I mean, this is important. You have to think how to optimize the coverage of the material and the thinking that the students are doing. And in that first experiment that I showed, in fact, that was carefully set up to test if you could cover the same, material in the same amount of time and then test at what you were learning. And in fact, in that experiment, the research-based teaching that had the students working through problems didn't cover quite as much material. It covered about 90% of the material. But as it turned out, the students did better. The students in the research-based class did better on the test of the material that they hadn't seen than the ones in the actual lecture class. So covering the material is not the same as having the students learn the material. And so, but that said, you do have to think quite carefully about optimizing how you use time in the most effective way, and how much, what things you can have the students do on their own outside of class, and then what you do most effectively in class to get the optimum benefits. And it's not a trivial sort of optimization thing there, but at some level, what's really important to recognize is you're teaching students to think. You're not and they can learn and do a lot of things on their own in terms of specific material. It's the thinking about the material that matters.
Thank you. The second question is, teaching methods in Myanmar cannot focus on research-based teaching due to lack of capacity in research work. Especially most of the staff do not have capacity on this method. Could you suggest to us, regardless of research work, which teaching style would be more effective for interactive pedagogical teaching?
So I think the key thing is that even if you don't have a lot of research in your universities and so on, that really doesn't matter. You're still trying to have students learn to think, to solve problems. And so there, I think, most reasonably educated faculty members can still understand how to teach this way. Now, learning to teach this way does take some effort and some time, but it's not that hard. It's frankly, because it's newer and sort of less advanced, it's a lot easier to learn the research on learning and teaching at this level than it is, on the frontiers of physics or chemistry. And and so you can go and you can look, you can read the materials, look at the things that we have, but also you need to have at your universities, you need to have training programs that help the instructors learn to teach this way. And the references I gave, and particularly the the Ambrose reference and my own book and the resources at the CWSEI website at UBC, those all have things where there are some training programs for faculty and teachers to learn to teach this way. So I think that's probably the thing that's most important, is to have the universities support the their teachers learning to teach better.
Thank you.
And I think what we've seen is that people all over the world and teachers all over the world can learn to do this, and they get better results. But there's obviously institutional barriers and challenges and cultural differences. But
Thank you. Another question that I think is quite pragmatic is there any appropriate model for those students with uneven prior knowledge and experience who have changed from one research field to a totally different field, and how do you address that?
so this is a tremendous difficult, or this is at some level the biggest problem that any good, well-trained teacher still struggles with, is that you have this range of backgrounds of students in your classroom and how to properly help all of them be most successful. And so, I can't give you any magic way to make that work. It's something that everyone struggles with. I can say a few things the research tells us is, first, there are certain methods that seem to be the most effective at covering the widest range of students. And so the kinds of methods that I talked about, where the students are working through problems, getting targeted feedback, that addresses, that's more adapted to their level, because the instructor is having a much better idea of what level the students are at, and working in groups. And so that the best students learn better because they're teaching the less prepared students, and the less prepared students are learning better because they have someone who can give more in guidance at their own level. So we see these methods work better than the traditional lecture approach to a wider range of preparation. But having said that, there is a limit on how much of a range you can have. That no method can be wonderfully effective if the material is just way beyond what the student's preparation is. And so one then has to kind of have some way of figuring out what's possible for what their preparation is, and match it. But I don't mean to make this sound easy, because I think it's every institution, every time, in every setting and every country is trying to figure out, because you have a big range of student preparations, how to make it work best for those. And there's no simple, easy answer to that.
Thank you. Perhaps this is personally relevant as well, this question. Do you have any experience teaching Asian students? Because Asian students are very weak at asking questions or getting involved in group discussions. What is the best way to motivate Asian students to ask more questions?
I'm gonna take a little time to tell a funny story but it really does make an important point here because so first I'd say I have quite a bit of experience with Asian students because at the University of British Columbia, in fact, they have students from a variety of Asian countries there, but it's the majority of the students actually have Asian backgrounds. And so where I was there and we led this big program in changing teaching, we got a lot of research on this. But the funny story is when I went I gave a series of lectures at University of Tokyo, not a few years ago. And so, and I'd given lectures to the students and had some examples teaching them. And then the next day I gave lecture to the faculty and I got this exact thing of the faculty saying, well, these methods may work in the US, but our students would never say anything in class. You couldn't get this interaction and so on. And the funny thing was, I had just the previous day given lecture to the students, and where they were all very interactive and very lively in discussions. And the difference, and it was really quite clear as to what was going on, is that in the lecture to the students, I had set it up and made it very clear that the norms of their behavior were different on what they were supposed to be doing. And so it's, Asian students are actually more willing than US students to work together, to talk to each other. This is what in fact, the culture is more about working collectively. And so they don't say anything in the classroom because the norms of the classroom are set that you're not supposed to be saying things, you're not supposed to be talking. But if those norms are changed, and I found in my lecture, it was quite easy, that, okay, they came in and, well, they weren't supposed to be talking to me. They were supposed to be, I just stopped. I gave them something they were supposed to talk to each other about and write down answers for. And they were supposed to write down what answers they came to as a group. And I just stopped talking and I walked around and listened and looked, and when they didn't have anything written down, I'd say, how come you're not talking to each other? You're supposed to be doing that. And as soon as it was very clear that that was what was supposed to be happening in the classroom, they were completely willing to do it. And in fact, at University of British Columbia, we found that in these teaching methods, when we put them into practice, all the students found them, after we did it, got them comfortable with it. All the students liked it and all the students learned better. But the Asian students actually, and particularly the Asian students from the cultures where that was the least likely to have them say anything in class, they liked them the best because it made the biggest change to them about how their learning experience was happening. So I think it's a question of simply understanding how if you have to make sure the classroom it's very clear that the classroom has changed what the expected behavior of students in the classroom, not just expected, but desired, has changed, then they're actually very happy to change and very happy to interact with each other, because it's not that they don't do this, they do it all the time. It's just in the classroom where you have a professor who's not supposed to be interrupted. That's the norm that they're used to. As soon as you change it, they like it. So.
Thank you. There's one question which is related to one of your slides. Wouldn't emotionally evoking pictures or graphics motivate students to learn?
So there's actually studies on this that show exactly the opposite, and it's and and it does have to do with this divided attention, that things that really capture attention aren't capturing in most cases. It's because they're appealing to sort of basic emotion things that's quite distracting, that distracts them from thinking about and focusing on the science, which isn't the emotion and isn't the differences. And so yeah, so in terms of the kind of ongoing learning, they won't. Now, on the other hand, they can be motivational. So this is now to serve a completely different purpose. For example, I'll take the example of making people want to learn to become a doctor, showing them pictures of people suffering and then medical science making them better. that's that can be quite valuable for inspiring them to say, okay, I'm going to go off and learn to become a doctor and so on. But that's not helping them actually learn the science. When they're in the process of learning the science, having those pictures might, where you want them to understand what's going on in the cells and how drugs are affecting it, those things about suffering people are just distracting at that level. So it's important to separate out the motivating people to want to do something from the actual thinking about it in real time and the learning of that science.
Thank you. So we still have a few more questions, and the time is almost up. I'll be very wary of the time. Um, One question is particularly very relevant to Myanmar. In Myanmar, uh, the participant sees that curriculum design is one of the big problems, which is really designed by the Ministry of Education, and it is based on time available in class. Um, and teachers focus on this curriculum to be finished within targeted time or period, but not on how much students can learn. In other words, to be finished, to get the curriculum finished is the matter, the focus.
Yeah.
When I compare to student-centered teaching method, curriculum doesn't matter. Just focus on how students learn and how much they get. What would be the solution for this problem?
So, uh, as there's two different answers to this. I mean, one is that you can, I think at one level, curriculum does matter. There's a certain set of things you want students to learn and, learn about particular areas of physics or chemistry or biology that are important. And so you do have to pay attention to that, but you have to then think quite carefully about if you want students to master something, what you do and don't really need to cover in the classroom and things, so some things you can have folks in the classroom to really optimize their learning, and then other parts that are just sort of then applying that using new content they might be able to go and get at home and do reading the book and so on. And so there's trade-offs you can make to kind of cover curriculum best in different way in the given amount of time and different settings. But that only goes a certain way. There's also, many situations I've seen where there teachers in different countries or different in even in different units in the country are required to do certain things that are not optimum for learning and maybe unrealistic, that their students could actually really learn these as opposed to just memorize a few things. And I can't give you an answer to that. That's really something that is determined at in the society in which it's set. And so I can't tell you how to change the Ministry of Education in Myanmar. That's
Thank you. Um, So this is really interesting. This question, the participant wants to know how to implement a research-based learning approach in the traditional style of learning, like religious studies.
So uh, now I'm going to be very careful because no, one of the things that I spend my life doing is telling people that we have research on doing things. You have to pay attention to the research and not make wild claims. So I don't have any research on these other kinds of subjects, okay? And so I'm going to now be very clear that all the stuff I said before, I could give you data and so on to back it up. Here, I can't give you data to back it up. I can only extrapolate from our general studies of expertise. In our general studies of expertise, we see that expertise in a field and the discipline itself is really based around a set of decisions that people make in that field, and the people in that field have kind of agreed that there's certain kinds of ways of making decisions, certain arguments and logic and information that it's based on that establish what expertise in the field really means. And so what I think is likely true, but I don't have data to back it up, is that you really want to look at, in, for example, religious studies, you want to look at people who are accepted as scholars in that field. What are the as the experts, what are the decisions they make and how do they make those decisions? And then it likely would work best, to work is to have students be given those same kind of questions, at the appropriate level, and they have to kind of make those decisions and then get feedback on those decisions. Uh, and that's the just think about, you want to exercise the brain to strengthen it doing certain things uh, that are the desired learning out educational goals, that's likely to be right. And that's just extrapolating because of the way we see the brain. Actually, we understand enough at the basic brain level of how learning is happening.
Thank you. I'll take only two more questions from here. Um, I think that this person is probably from a high school. What is the major difference between research-based learning approach at college level versus high school level?
So there's probably very little difference. The main thing that I see is between the research. I'm one of the very few people who actually uh, knows some about the research at the lower grade levels and the university level. Those are usually in most institutions completely separate. The people who look at them very differently. So what I can say in general about the research at the K-12 level is there are just more well, both the research, but also in the teaching, there are just more factors that matter at the lower grade levels. So you're dealing with at the university level, we have a selected set of the population. They're in a specialized environment. And so the background, things that are really important at the lower grade levels of background and environment and direct situation and emotional issues just are more important. And we have the great luxury at the university level. We don't have to worry about them so much. But in terms of, and and it also gets into what your goals about learning are that differ. At the high school level, though, that's close enough to the university that there's not so much difference. And so I would argue that almost certainly the teaching methods that I've talked about that are valuable at the university are going to apply pretty well at the university, at the high school level. You may have some particular factors you have to deal with more, motivation and what's motivating students to put in the work required is likely somewhat different. But a lot of most of the same practices and principles are going to work pretty much the same, but you will have likely also have some differences about your student population and what, some additional factors that you probably have to worry about to make sure these things are effective in that case. But there's a large amount of overlap there. Once you get to lower grade levels, it gets much more questions about whether it would really apply so well.
Mm. Uh, I'll ask the last question from the participants. Which theory do you normally use for assessing students' progress or growth on learning materials in the classroom, specifically on cognitive process, critical thinking skills?
So this is something we study. Actually, I study a lot, and so I'm this. You'll have people who can disagree with me, but I'm pretty convinced from our research that there's really no such thing as critical thinking skills that are independent of a discipline area, and that anything, whenever people talk about critical thinking skills, that's this kind of skills they talk about and think are important always involve recognizing what the relevant information is and using it in that context to solve problems, to answer questions. And so that fundamentally means as soon as you're deciding on information, that's bringing in the discipline. And so there's critical thinking skills, but they're always coupled to disciplinary knowledge. And so when I am looking to how assessing critical thinking skills, I'm always thinking about assessing critical thinking skills in a discipline. And that means giving the students decisions to make. These are core problem solving decisions, how they can solve problems in the context of the discipline, but trying to think about the problems that are realistic, real world, not so artificial, but at the right and a reasonable level, and covering the material I hope the students should have learned. And that's the best way of assessing how they're developing intellectually.
Thank you. And if I may end today's Part Me Talk series with the last question of my own. Um, I always struggle as a teacher, to use one kind of inquiry method that I learned in classes, like some seminar classes in which they use a Socratic method of inquiry questioning,
Right.
and then trying to use that in activity-based or project-based or research-based learning in science. And is there any way for science teachers to use a Socratic method um, in um, in activities or research-based projects?
Yes, but one of the troubles with the Socratic method of posing questions to the students, okay, when it's done well, each student is thinking about how to answer that question and, triggering them to be thinking about what you want. When it's when it's done poorly, and in most cases, this is what happens, is instead of thinking about how to answer the question, the student's thinking about oh, I hope I don't get asked this. I hope they don't call on me to answer this. Oh, I hope they don't call on me. Don't call on me. And if they do call on me, kind of, oh, I don't know the answer. And so the instructor goes off and asks somebody else. And so if you kind of look at the way I talked about going through and teaching this way. In many respects, it is like the Socratic method, but it's a more structured way of, here's a question you've got to answer, and everybody has to answer that question themselves. So they have to write something down or use their cell phone to send in what answer they think it is. And so it really is in some sense, the highly effective Socratic method. And it's just how to scale it up. So, if you make it down to smaller groups, it's still the same thing of posing a question or a problem to students that they have to answer, and you see how they answer, and you give them feedback on that, and you ask them the next question to probe their thinking in more ways. And so it really is, and of course, if you just have a few students, then it's much easier to make it part of an ongoing discussion. But you have to recognize that in terms of what you want to have happening in the students' brains, it's really very much what we're thinking about here. So, and I'll just leave you with one final kind of model or principle to think about when the teaching is, at some level, all of this goes back to what is the best way to teach that we know about. Well, that's a one-on-one tutor. That's what parents do with their children. It's what, back when we were, people living in caves, trying to teach people to hunt. They'd have the teacher would give the student, say, well, okay, so practice throwing your spear to try and hit this mastodon or whatever. And and uh and then when they talk about, and but you see, you went off to the left, so how should you correct that to make it go more in the right direction? And so it's this kind of one-on-one tutor of practice and feedback, and it's not an accident that all the things I'm talking about are really just ways to try and scale that up to work in more people, because that's how we evolved as as organisms, to complex animals, to teach and learn from each other. And we're just trying to, so the things I'm talking about are really just scaled up versions of that basic cognitive processes.
Thank you very much, Professor Carl Wieman, for today's talk. Um, I when I come to the States, I wish to visit Stanford again, and I'd love to meet you. But I'm really grateful for giving us your valuable time to our Myanmar Public University faculty members. I hope that um, the presentation that you provided and your talk are very much useful to Myanmar Public University faculty members, even though we have very different many different constraining factors. But I believe that there are ways to incorporate.
Yeah, and so I talked about doing lots of different things. You don't have to do everything at once. Just start to bring in the basic principles and think how you can bring it in within your environment, within your students, and sort of slowly build this. And it's just recognizing that we do know more about how the brain learns, and we can help start moving more and more to optimize that. So thank you. It's been a pleasure talking with
Thank
you.
you so much. And thanks a lot to everyone who has come in this early morning to join the session. And we will be, I believe Professor will share the presentation with us. And if you wish to get your presentation, you can email us and we'll share it. And we can also share it on our Facebook, Parma University Facebook page under the video. And I wish you all good Sunday. Um, and thank you very much for
Good
attending.
night, or good morning for you, good night for
Good
me.
night to you.